Thank you, Fabian. Stephan and I, we handed in this talk together, but as you can see, there's no Stephan here, so I'm sorry for that if you expected him to come. But he and I had some very helpful discussions on how we structure this, and some of the topics overlap with what he said in the keynote. But this is going to have, you're going to see some slides that look the same or are the same, but this is more the lower level details, if you will, of the broader vision that Stephan outlined in the keynote. Before I start, I want to say that this work that I'm presenting, this is work that is going on in the Apache Flink community, and it's the work of a lot of people, and I maybe have forgotten some people, but it's people from the Berlin teams, Timo and David, and people from the teams in China, and all of these folks are working together to make this happen. As you will see, this requires changes all through the stack of Flink, which is quite exciting. Also, I'm basically talking about things that are going on in the community. There's design docs for some of these things. There's mailing list discussions. There's maybe in-person discussions about these things, but this is basically my understanding or our understanding of the roadmap or where things are. I mean, Flink is an open source project. I don't control that. I can't set the roadmap for that myself. Just keep that in mind. So before we can talk about, I mean, the title of the talk is Batch and Stream Unification. Before we can do that, let's talk a bit about what actually is batch and stream processing. So you have seen this slide. We say batch and stream processing, they are quite related. So we say that naturally all data that you have somewhere is a stream. There's no such thing as a bounded data set, if you will. Bounded data sets are only cut out of an unbounded stream. So we think bounded streams are the natural thing, and then bounded streams, which you have in batch processing, are cut out from one stream. But even though we say that bounded streams are basically a subset of unbounded streams, there is still different use cases and different approaches that you can take to things, and we will see later how that influences the design of a system such as Flink. So there's, on the one hand, or you can think of it, what changes faster, if the data changes faster or if the application logic changes faster. So in what we typically call stream processing, the data changes very fast, so you process a stream of data in real time, but you have some query sitting there, some pipeline where you apply a machine learning model or where you do some analytics. And in those use cases, it's usually important that you get data fast. So you have real-time data incoming, you want results in real time. On the other hand, batch processing, there the data changes more slowly. You have your data sitting in some HBase, you have it sitting in what people call data lakes. The data doesn't change fast, but you want to do lots of ad hoc queries on that data. So data sits there, doesn't change. You run different machine learning models to derive, or machine learning programs to derive models from that. You want to explore the data that sits there, which is quite different from stream programming. So traditionally, we call the one batch and we call the other one streaming. I mentioned that in stream processing, what you are often concerned with is latency. So you have your data coming in, and you're concerned with when you get the first results from that data. And for this, one thing that has become quite popular in stream processing is this concept of watermarks. I'm going to get to that. But the more hands-on or graspable explanation for that is actually given with this Star Wars example. So at the bottom, we have processing time. That's when those movies were released. And on the top, we have the episode numbers. So imagine some friend asks you, give me a summary of the Star Wars movie series. He's quite excited, it just came out. And you say, okay, let's wait until I have the data come in, and then I can give you my results. So you sit there and wait. Then the first 3 episodes come out, which are actually episode 4, 5, and 6. So you say, should I give him the results now? Then they are somewhat incomplete. Or should I give them now? Then the latency is very high, but the accuracy is not that high. So maybe you wait. Then time progresses. Then you see episodes 1, 2, and 3. And then you think, now I've seen 1, 2, 3, 4, 5, 6. Now I can give him a summary of what Star Wars is like, meaning you have good accuracy at that point, but you have very high latency because you saw the first 4, 5, and 6 quite a while ago, and so it took quite a while to get there. Then episode 7 comes, fine. Then you get the curveball that is Rogue One, which is what we call late data in stream processing, because the watermark has already advanced to, say, episode 7, and then, boom, episode 3.5. So what you do in that case is you either throw it away, late data, we don't care, or you retract the thing that you did earlier, or you outputted it in some other stream. And then we have episode 8, and everything is fine again. So that's somewhat, you can explain it to your friends that way. We have basically everything in there. We have a watermark in there, we have out of orderness, we have late data, we have retractions, everything. The more formal way of thinking about this is, as I said, is the watermark. So you have on the one axis, you have processing time, which is just time progresses as you process your thing. And then you have event time, which is the time in the stream of data. And ideally, you would like them to correlate completely. So you would have, as processing time goes on, event time goes on, and you can produce your results because you know that you have seen all the data. But in reality, event time is a bit behind processing time. So if you want somewhat good accuracy, you will have to accept some latency. And this is expressed quite well with this concept of the watermark. And this figure is actually taken from this 2-part series of articles by Tyler Akidow that he wrote about stream processing. So if you want to know anything about these semantics in modern stream processors, watermarks, etc., this is a super nice series of articles about that. So just to summarize this again, in stream processing, or let's start with batch processing. In batch processing, we have all the data immediately, and we don't care about latency control. I mean, we have all the data sitting there, the job needs to run, and then it finishes, it produces a result. It's cool. In unbounded processing, we need to trade off latency versus completeness. And what we usually use for that, so we will come back to this later. What we usually use for this is processing time to allow us, or processing time timers to allow us early results. So in this Star Wars analogy, what you would do is maybe set a processing time timer for, hey, friend, I will give you an update in, say, 3 weeks. And then you just tell him the summary of the movies that you saw within that 3 weeks, no matter what the actual event time is, so what episodes came out. So he will have some result that is driven by a processing time trigger, but that is maybe inaccurate. And to understand what a system such as Flink needs to do when you process data, and then to also look at what we need to change in Flink to unify those two modes of processing, let's look at how data is actually processed in these different styles of processing. So let's say we have some data here. This could be in some files. This could be a message bus. And the events in these files are roughly ordered from older to more recent. So when we do stream processing, as I said, in stream processing, we are usually concerned with getting results that are up to date. So usually we want to process the stream of data in lockstep, if you will, with the watermark and produce results incrementally as we go. So how we process data is that we process it step by step in the individual files or individual topics or partitions. And then the watermark, which tells us how far we are in event time, processes along with that data. This has some consequences. It means that the data processing is limited by the parallelism that we have in the data. If there's two partitions in our message bus, or if there's only 5 parallel files, then we are limited to reading 5 things in parallel at the same time, or 2 things in parallel at the same time, because we want to make sure that we advance in event time at roughly the same pace. What can change is that the resource requirements change over time. So there might be more data in those topics, so the stream processing has to react to that and maybe have more parallelism or less parallelism. And then I mean, I got lazy, and that's just, that's how it is. But for batch style processing, as I said, we don't care about the strict latency or that we always have results at the time when they occurred. So we are not limited by having to go through the data, through our message bus in event time order. We can just read all of the files at once if you want. If there's 100 files, we can just say, super big cluster, parallelism 100, read all of them files in parallel, and then done. We can produce results because we're not restricted by this watermarking, latency, processing time, anything. So what we do is just read everything, watermark, semantically goes to the end, and we're done. So that's, we'll come back to this later, but that's an important distinction. In stream processing, we process as we go, and we use processing time timers to produce early results if we want. In batch style processing, we don't have processing time timers for early result, but we just semantically have the watermark at -infinity if you want. We process everything, and then watermark goes to positive infinity, and then we can produce our results. Say our aggregations that are on time windows or something like this. This way of executing also has implications for the system that you're using to process the data. So in a more streamy execution system, so this is let's say a DAG of operations. So we have some operators, say sources at the beginning, then some transformations, then let's say a group by, and then some things. So this could be MapReduce if you want. In a streaming system, because we want to produce results in real time as data comes in, all the parts of our processing graph have to be running at the same time. In a batch world, what we can do is just, we can process data step by step. So what we can do is we just bring the sources up. They can have the massive parallelism that they need to read. Then the next stages come up, they read, the sources can shut down, so we relinquish resources. Other parts come up, and the system goes in stages through the processing, which allows it to spend more resources on a given stage. I mean, in a streaming execution style, all the resources are shared by all the operators, all the stages that are running at the same time, and in the batch case, we can optimize it for really the maximum throughput at each individual stage. So that's an important thing that we should keep in mind for later. And this fact that, yes, batch and streaming can be viewed as the same thing, where one is a subset of the other, but this fact that there's different execution styles and different requirements, this is, I think, one of the main reasons why we have these different systems, why stream processors have not eliminated batch processors. It's these different requirements that come just from historical needs. I mean, back in the days, people didn't think about stream processing. All they wanted was batch processors. And this different potential for optimization that you get when you have, when you know that your data is bounded and you can just execute it in a different way. That's, I think, the main reason for why we have these separate systems. And also why Flink has a DataSet API and a DataStream API, why it's not just one API. So now, before we go into what the current stack will look like, what the future stack will look like, let's look at what the current stack looks like. So in Flink, for our purposes, there's the bottom layer, which is the runtime. This is the lowest level of the system. So this deals with deploying operations on distributed machines. This deals with fault tolerance. At this level, you have something that we call tasks. These are operations that can run on task managers. And the graph structure, say, that connects these different tasks and has the network connection patterns, we call this the job graph. Then on top of this, we have the DataSet API and the DataStream API. And in the DataSet API, we call these different operations operators, and they're executed by drivers. And the graph, we call it an operator graph, and there's visitors that can transform this graph that we get from the DataSet API to the lower level job graph that is needed for executing it on the Flink runtime. In the DataStream API, we have a thing called stream operator. This is how operators implemented. And there's a graph of stream transformations. And then there's these giant monolithic translators that translate a graph of stream transformations to a drop graph that we need for executing it. And then on top of that, we have the table API or SQL API, which is, it produces a graph of logical nodes that capture this declarative style program that we have. And then there's translation paths that translate the SQL or table API program to a dataset program or a DataStream program. So from a systems design perspective or just from a code cleanliness perspective, this has some issues. So each API has their own internal graph representation, so that's quite a bit of code application. There's multiple different translation components from these different graph representations to other graph representations. And the Stream API actually has one intermediate representation that is just there for historical reasons, but it's still there. There's different incompatible operator implementations. So the DataSet API has this thing called drivers. And as I said, the Stream API has these stream operators. So in the APIs, if you say map, this will actually be executed by completely different code underneath. So there's a map operator for the Stream API. There's a map driver for dataset. For flat map, there's a driver and a stream operator. And then again, at the lower layer, at this runtime layer, there's different tasks that are executing these stream operators and these drivers. So there's a lot of duplication going on there. Then for table API, you have these two different translation paths from to the DataStream or DataSet API. So for a project or for a select, there's one for each. And for connectors, the same. There's for the DataStream API, you have the source function, and for the DataSet API, you have the input format. And there might be a Kafka connector for DataStream, but there might not be a Kafka connector for DataSet. There's an HBase connector for DataSet, but not the other way around. And same for Table API. Table API needs connectors for these two different systems. So that's fine for users. Usually it just means that life as a Flink developer is a bit harder because we have these two separate stacks, connectors, everything is duplicated. But if you are a user of Flink, this means that there is slightly different APIs. So if you just glance at it, dataset, DataStream programs, they look roughly the same, but they have slightly different capabilities. As I said, there's different sets of connectors that are supported. There's different performance characteristics, different fault tolerance behavior. The scheduling is different, where in DataStream, everything's scheduled at once. DataSet, stage-wise. With Table API, the cool thing is you only have this one API, and it can translate to DataSet or DataStream programs. But the set of connectors that you can use is still dictated by what underlying API you use. If you write a SQL program and want to read from Kafka, it has to translate as a streaming program. If you want to read from some batch sources, it has to be a dataset program. And someone has to have developed that connector for that underlying API that you want to use. And another thing is you can't combine those. So you can't say, read your historical data from your HBase and then combine it with the real-time data from Kafka coming in. You can't combine them because there's not a set of connectors for one API that would allow you to do that. And a bit of a more softer problem, which stems from this developer inefficiencies, is that just less developer power will go into one specific API. I mean, there's people working on the dataset, there's people working on DataStream, there's people working on all of these different connectors for the different implementations. That mean that developers are somewhat spread thin over all these different duplicate APIs, translations, connectors, and so on. That could lead to less features being developed, lost performance, or that bugs will be fixed slower because you have to deal with things all over the place. So it would be cool if we didn't have all this duplication. So let's look at where things are going. So we say this often. I said it before, batch is a subset of streaming. So can't we just say, we have the DataSet API, we have the DataStream API, just deprecate the one, say we only use DataStream from now on, boom, done. We can go home. So the solution will be something like this, but it is more complicated in the details, because the DataStream API is not as efficient at batch programs as the DataSet API. So let's look at what, yes, we just eventually remove one of them, only keep one of them, but we have to do a couple of things before we can actually do that. So yes, what I said is DataStream API functionality, I think, is a strict superset of the DataSet API. There might be some wonkiness. So in DataSet API, you have this group reduce where you can get an iterator of everything, or you have a map partition for people that know. This, you can do this in the DataStream API, but it's a bit wonky. So a group reduce, for example, would be a window with a window function and a global window. It would be the same functionality, but would be way less efficient than doing it in the batch API, because in the batch API, we can do this in phases. We sort the data, then we stream it in. In the DataStream API, you would have to have your data in RocksDB, and data access would be super inefficient for this. So in order to know about the fact that we have a bounded stream, we will introduce, or should introduce, this concept of a bounded stream to the DataStream API. And this would then just, the DataStream API would then just know, this is a bounded stream. I can do things that are efficient for batch processing in this part of the pipeline. And semantically, if you recall from earlier, what this means if we have a bounded stream is that we don't have processing time timers, because we don't need to deal with latency or early results, and that the watermark in those parts of the computation would just jump from -infinity to +infinity when the processing is done. So semantics are somewhat clear on this one. Under the hood, this means that the translation and the runtime features need to be enhanced a bit to use this additional optimization potential. But once we're done with this, the cool thing is that the DataStream API, as it is now, is just the generic case that always works. So it works for streaming programs. It works for batch programs. So you have feature parity for this. But the fact that you have a bounded stream is just an additional thing that enables more optimization rules. Then it just allows the translation steps and the runtime to say, cool, this is a batch join. I can use a hybrid hash join for this one, because that's way more efficient than doing all my business with RocksDB. So we automatically get feature parity between the two APIs, different connectors from this, and get the additional performance that we get from batch-style execution. But more stuff we have to do for this, so the sources have to be updated. I'll come to that in a second. I just want to highlight this one because a lot of people are talking about this. So this would be a typical use case that is enabled by this batch streaming use case. So actually at last year's Flink Forward, Greg Fee talked about this from Lyft. This use case where you have your historical data sitting in S3 somewhere. You want to read this and bootstrap your stateful operation, and then you want your program to switch over to the real-time data that is coming in from Kinesis. So they developed solutions to work around this, but they have to, because Flink itself, the DataStream API, doesn't know about bounded sources, unbounded sources, and so on. So that's actually quite interesting. And for the execution, what would happen here is that, say, you first execute this batch part on the right, so you execute it in stages, maybe you execute that source, then the operator, then the other one, then that is done, and then the system can bring up that streaming part and shut down the other part and continue processing. So you are resource efficient because you don't need to have both of them up at the same time. Plus, the naive way of doing this just in the DataStream API would mean that the left part is running at the same time as the right part is running and stealing resources from going through that historic data that you don't need before that historic data has been completely read. As I said, there will be under the hood changes required for this. So there, as I mentioned, there's these different graph representations that we have underneath these APIs. And for the DataStream API, we need to beef up that graph structure to allow it to carry that additional information about boundedness. And then other components like translation, so the component that takes this graph, translates it to a lower-level drop graph, will need to take that information account. The scheduling components of Flink, the parts that say, okay, we schedule these operators and then these other operators, that has to be updated. The network stack has to be updated. Memory management has to be updated. So we need to know what operators need what amount of memory so that we can know, because the scheduler knows which operators are running at a given time, and then we can tell these operators, look, you can use this much memory for your hybrid hash join, and then we efficiently use the amount of available resources. And so once that is done, the stream operators itself, the operators, they need to be updated to support batch-style execution. So we look at that on the next slide. So if you recall earlier, this batch-style execution is implemented in a pull-based way in Flink. So this is how most databases were or are implemented, is that they pull data from the upstream operations because they know what data they need. So a hybrid hash join, for example, knows I first need to pull all the data from the build side, and then once that's done, I can switch over and read from the probe side. Because the operator needs to know what algorithm it's using. That's how things are usually implemented. But on the streaming sides, operators are implemented the other way around. They have this push-based model where the stream operator is just sitting there, and then data is just pushed into the operator from both sides. The operator doesn't know where data is coming from. It just has to be able to deal with that data. So it has to have RocksDB for state, say, and then it just pushes things into the state and joins and needs to hope that memory or disk space will be enough for this. So there's this image of the dog drinking from a water hose that some people may know. That's how it must feel to be a stream operator. You just sit there, the water is coming in, and you just somehow need to deal with it. So what we need to do for this is actually, it's already started, so the Flink issue is up there. So people are working on changing the stream operator to allow it to tell the system which input it would like to read from. So we can't change it to a pull-based model because then we can't support streaming cases officially anymore. But with these updates, the operator can say, look, Flink, I need to read from this side first because I'm building a hash table here, so please don't give me data from the other side. And then if the system thinks that this is okay to do, it can honor that request from the operator. And then in this way, we can implement these batch-style algorithms using a stream operator that can tell the system what it needs to do. And another thing that I quickly want to mention is that for this to work, we also need to be careful in the network stack because you can build graphs that have what people call deadly diamonds of death, where you have one operator, then you branch out, and then they join again. And if you then say block on one side of the operator, it backpressures the other operator, this backpressures the other operator, and then you don't make progress on the other side, and in this way you have yourself a distributed deadlock, and then you won't make any progress anymore. So translation parts, network stack, all of them have to be updated to also make sure that such a thing doesn't happen. So now, the second to last thing that we look at is the source interfaces. So I mentioned that we have duplication in the graphs, we have duplication in the operators, and we have duplication in the connectors. This is just because connectors work in different ways. It's similar to how the operators are pull-based and push-based, the same way the connectors are implemented in that way. So for batch use cases, we have this thing called the input format. And this is how you implement connectors for the DataSet API. And what this interface does, it basically allows the input format to enumerate the splits, so the ranges of data that are available in the input files. And then it can assign those splits to tasks. And then when we need to read from those splits, we have an input format, we give it a split, and then the system pulls from that input format until the split is fully read. And I will have a slide that shows how this looks in execution. And for the streaming API, we just have a source function that has a method called run, and that is just called by the system, and that implementation of the source just has to do what it needs to do. We will also look at that in a second. So first, let's look at how batch processing works. So you have a bunch of task managers sitting there. They run parallel instances of that input format. So in there, this is an input split. So you guys over there in the task manager, and this side is the job manager. So what happens when we process data from a source is that a task manager is sitting there. It doesn't do anything. it asks the job manager, please give me another split of data that I can read. The job manager calls this createSplit method initially and knows all the splits of data that need to be read. And then it gives those splits to the task managers for them to process them. And this way, Flink knows about the splits and can be clever about scheduling and sending them to the right task managers. We can process them in any order we want. And processing, as I said, pulls data from the splits. The downside of this is that the input format knows nothing about watermarks, timestamps, checkpointing, anything, so this doesn't really fly for streaming. On the other side, in stream processing, the source function is just, it's in the task manager, there's a source function, and then the system just calls this run method and says, do your thing. I have no idea what you're doing. What this means is that the source, they have to manage their run method completely on their own. They have complete flexibility how they want to interact with the system, so they can do efficient access to Kafka, they can read from multiple partitions, how they need to read from Kinesis, they have control over the threading model, everything. This means Flink has no idea what's going on, so it can't be clever about scheduling or some other things. And it means that the sources have to implement some features for each source themselves. So per partition watermarking for Kafka, for example, implemented in the source. Idleness tracking has to be implemented in the source. Event time alignment, making sure that we don't read things too fast, has to be implemented in the source. So that's a bit of a bad thing. So what we need to do is have a unified source interface that allows both of these use cases. So it must support batch and streaming use cases. It should allow Flink to be clever in how we handle event time watermarks, snapshotting. And also it should enable us to do new features. So we should have this idleness detection, which is a feature that allows us to advance the watermarks even if a source is idle and no data is coming in. And this event time alignment, which makes sure that we don't progress too fast on one source. So we saw this morning in the keynote that the trade desk had these problems with sources advancing differently fast in event time. So one thing you can do there is to make sure that you read data in alignment. This is a feature that people are working on. So actually, he also mentioned this Flink issue, and he mentioned that there's some first work being contributed for this already. So with this interface, maybe I should mention what it is. So basically what it is, it takes the parts from the input format apart and enhances it with the functionality that we need for streaming. So we have a split enumerator, which is the thing that discovers splits, and we have a split reader, which is what reads splits, and both of them support snapshotting, and both of them have functionality that allows them to deal with watermarks and event time, and so on. And what we can do is, for this more batch-style execution, the job manager would run an instance of this split enumerator. These split readers that are running on the task managers, they request the split, the job manager gives it to them, they do the processing. So it works pretty much the same way as the old format. Flink can be clever about scheduling those splits. It knows what's going on. Yeah, that's pretty easy. The split readers, they deal with emitting watermarks. And because we have, logically, we know that these splits correspond to partitions, Flink itself can do, for example, per partition or per split watermarking and idleness detection and this event time alignment, because Flink is what drives the reading from the source. It's not a run method anymore where we just say, cool, do your thing, you have your run method, but Flink knows what's going on and is requesting data from these splits. And just to quickly mention it, so this first mode of operation was there's a split enumerator running on the job manager and the readers on the task managers. What you could also do is just have the enumerator running as a source in Flink, so be its own operator, and then it just sends push-based, it sends these splits down to the readers for them to execute them. So with this new interface, we actually support different types of operation, and both of them can be implemented in Flink and used depending on whether we're in a more batchy way or a streamy way or what have you. So this is actually the end of the talk almost. So for Table API, we are pretty golden actually, because Table API is already unified, so that's easy. One thing that we need to update is that we need to update the translation steps of the table API, basically to not translate to dataset or data streaming, but based on what we know, use these optimization rules to either translate to a stream operator that does a more batch-style execution, so uses a hybrid hash join, or does a more streaming-style execution. And we have the same property that we get in the streaming API, that streaming is basically the generic case that always works. And if we know that it's batch, that it's bounded, we can enable additional optimization rules. So that just means we use different operators and different scheduling, but we are still in the same graph structure and still in roughly the same framework that we have for streaming. Plus, oh, this is a bit too far. What we get from this source unification is that sources will just be unified as is. We don't have to do any extra work for the table API. You also saw this mentioned in the keynote, so there's already work ongoing to do this for the table API. So this tier issue is the thing that is tracking that progress. So it's merging these table API enhancements from the Blink fork from Alibaba into Flink, and they already have some or most of that stuff in there. So they have an updated stream operator interface. They have this table API translation that does translation based on whether it's bounded or not. And then the future stack will be, we have the runtime, we have this beefed up stream transformation DAG and these beefed up stream operators, and then we have the DataStream API, which can do batch and streaming, and it's the more physical API, and you have the table API, which is the more declarative style API, and both of them sit on the same underlying abstractions. Oh, sorry about that. So in closing, the semantics are quite clear about this watermarking and processing time and lateness. For some of this stuff, there's Jira issues that you can look at, or there's flips. Flip is Flink improvement proposal. So these are design documents that you can look at in the Flink wiki. Some of the things are just in the heads of some people or hidden in some mailing list discussions. And as I said, this requires changes through a lot of things. So I mentioned graph and operators, but there's a lot of stuff in deployment, network stack, scheduling, fault tolerance that I didn't even touch. So this would be several other talks, I think. But the nice thing is it's an open source project. You can look at the discussions if you're interested. And I think this is going to be quite nice. When we have this unified stack, we can be more efficient, and people get this additional benefit of just being able to use connectors that they want in this unified way. Cool. That's actually it, yes. Thank you. I think I overdid it a bit, but maybe we have some time for one question. I don't know.
Yeah, I think we have time for one or two questions.
You can find me at the booth if you have any questions, also, and be outside.
So, any questions?
So how does the unified architecture deal with iterations? Will it improve it, or not change iteration support, or make it worse?
That's a very good question. So for those that don't know, iterations is a way in the DataSet API, you have these iterations where you can send data back. You can basically have a back edge in the graph. You need this for some machine learning models, for example, PageRank or something. In the DataStream API, there is support for iterations, which is quite weak because it doesn't work well and it doesn't work with checkpointing. That's maybe what you're hinting at. But yes, I think we have to, there's no specific plans, but it's quite clear that we need to do something for making sure that we can do these iterations in the streaming API in a good way. Because I think Xiaoshuan, I think right now in parallel to me, he's talking about table API and machine learning, and I think in a bit he's having another talk where he also talks about this, about implementing machine learning on top of the table API, and for this we need good support for iteration. So there's quite some motivation from people to make iteration support work well because they need it for these machine learning things. I think we're getting nervous.
One more question, maybe? No? All right, then.
You can find me outside. Yeah. You can find me outside if you want.
Yeah. Excellent. Yeah, okay, let's thank Aljoscha again.